Hello, chemistry students. Professor Sean McMahon here, continuing chapter 6, molecules and compounds. So with the last lecture, we discussed how we can use a Lewis dot structure to draw covalent compounds and polyatomic ions because they are held together through covalent compounds. Lewis structure does a great job of giving us a quick, simple idea of what the overall molecule or polyatomic ion looks like. Today's lecture, we're going to take those 2D Lewis dot structures and again create 3D molecules with them. I highly recommend getting one of these molecular model kits. They're like 20 bucks. When I bought mine back in 1988, it was like 45. They're actually cheaper now. They last forever. It's plastic. So yeah, my kids even played with them as Legos. So that they have multiple uses. I would highly recommend. It's a good investment on your education. If you don't want to spend the $20, that's fine too. I actually have an option for you where you can go online and access a simulation to help you see the 3D structures of these Lewis dot structures that we're drawing. But let's kind of warm up and get to where we left off last time. So I want to draw the Lewis structure for this species. Now, what is this species? We should be able to name this. This is carbonate. This is one of the 5 non-metal 8s that I told you should know, okay? So the first thing is I got to count total number of valence electrons, okay? When I do that, I see that, okay, carbon has 4, there's 3 oxygen, each has 6, and then I have this 2 negative. And remember, for every negative, I'm gonna add electrons, and for every positive I would subtract. So 2 negative, I'm going to add 2. So that gives me a total of 4 plus 18 plus 2, a total of 24. So I did step 1. Step 2, determine the central atom. So carbon is the least electronegative element. I'm going to be talking about electronegativity in today's lecture. Basically, carbon is more metallic. So you're more electronegative if you're more non-metalish. Not that that's proper, but you're less electronegative if you're more metallic. So carbon is more metallic. Again, hydrogen can never be a central atom, but we're going to have carbon as a central atom, and I know that I'm going to have oxygens on the outer atoms, okay? So now that I've determined my central atom, I need to connect it to the outer atoms with single bonds, and I have to subtract the number of electrons used in those single bonds. 3 bonds, 2 electrons in each bond. 3 times 2 is 6. I subtract 6. I have 18 valence electrons. Now, with my 18 valence electrons, the next step is I need to distribute these remaining electrons, and the first thing I want to do in that distribution is make sure that the outer atoms, in this case the oxygens, have enough lone pairs to satisfy the octets. They all have 1 bond, so they would need 3 lone pairs, 6 more electrons to satisfy their octets. So I go ahead and do that, and I go 2, 4, 6, 8, 10, 12, 14, 16, 18. When I subtract 18, I see I have no valence electrons left. So if electrons remained, again, from last lecture, I would attach them to the central atom, but none remain. If no electrons are remaining and the central atom has an octet, I'm done. Carbon does not have an octet. It only has 3 bonds, 6 electrons around it. So what do I need to do? That last step, if no electrons remain, I need to remove one of the lone pairs on the terminal atoms because it's not really a lone pair and form a multiple bond. So I might choose, I might say, hey, I'm going to take this one and I'm going to move it right here. And I end up getting a structure of carbonate that looks like this. Well, sorry, I'm a little sloppy, but you get the point of it. Now, if I look, carbon has 4 bonds. So carbon has an octet and it's happy. And to finish the Lewis dot, I'm not a stickler for this, but some profs might be. You would put the brackets in the 2 negative. So that actually gives me this structure right here. Carbon's black, the oxygens are red. There's a double bond on the lower right. But you may also remember that, you know, on paper, this is flat 2D, but in reality, I can rotate things and get multiple Lewis dot structures. So I can rotate this 120 degrees, and then I would have the double bond there. I could rotate another 120 degrees, and then I would have the double bond there. And then another rotation of 120 would bring me back there. So I actually have 3 resonance structures. Why? I have 3 oxygens, and 1 oxygen has a double bond, so I could switch it on these 2D flat molecules to a different oxygen every time. If you're in higher level courses, you understand that there's something called hybridization theory. There's also pi clouds, but for this course, that's how we're going to look at it: double and single bonds. So what was the point of being able to draw all these Lewis structures in 2D, determine the number of resonance structures? Well, one is to realize compounds are striving, and atoms are striving for stability. That's why they form these bonds and trying to achieve an octet. But really, a big reason why we're doing this is we want to figure out the shape of these molecules. The reason why we want to figure out the shape is shape or form leads to function. You may have heard that before, maybe in biology. Form equals function. So like enzyme, it's a protein, it has an active site, it has a certain shape, it speeds up reactions because substrates fit into the active site and produce a product through an enzyme substrate complex. Well, that shape of the active site is critical for the enzyme to function. If the active site unfolds or it denatures, now it can no longer do it. You can think of it in terms of just form equals function in general, right? Basketball players have a certain shape. They're tall so that they can dunk a ball. They have a very different shape than, let's say, a sumo wrestler. That's just an example, but basically form, shape equals function. Now, the reason why this is called VSEPR theory, I used to joke around Vespa because moped, but VSEPR stands for valence shell electron pair repulsion theory. So when I think about shapes, it is due to this theory of valence shell electron pair repulsion. So what does that mean? Okay, valence shell. It are the valence electrons that are in the outermost energy shell that come in contact with other atoms where there's an overlap and they exchange electrons or share them. So the valence shell is what determines this chemical reactivity, right? The number of electrons in the valence shell. That's why with Lewis dots, we only look at the valence electrons. We look at the group numbers, okay? So that's why we look at valence shell. Electron pair. Well, to strive for octets, we want 4 pairs. Those pairs can be shared pairs, like in bonds, and we draw lines, or they can be unshared pairs, like lone pairs. That's where we draw the dots. And repulsion is the electrons are negatively charged, so they want to spread themselves around the atoms as far away as possible to minimize repulsion. So as a result, they get a specific shape. So the theory is based on the idea of, okay, well, yeah, we have what are called electron groups. Electron groups have electrons. So those can be lone pairs, single bonds, or multiple bonds, okay? So that is basically a way to think of it. These are gonna always repel each other. I like to try to make it simple because students get confused with electron groups and they think it's pairs, and that's not exactly true. The group is just when electrons are being spread between 2 things, let's say, for bonds. So it doesn't matter if it's a single, double, or a triple bond. So I always tell people, make it easy. You can think of electron groups as lone pairs and being bonded to another atom, and that whether it be a single, double, or triple doesn't matter. As if there's another atom, the electrons are going to try to spread around those atoms to minimize repulsion. So what can we use Lewis structure for? Well, once we draw the Lewis structure, we can look at the number of electron groups around a central atom to see how they're going to spread around that atom or that molecule to give it a shape. So each lone pair constitutes a group, and each essentially bond, it doesn't matter if it's single, double, or triple, every bond is another group. So here's a Lewis dot structure, and this is nitrogen dioxide. I believe we drew this, but if not, here it is. And what we notice is there are 3 electron groups around the nitrogen. And why is that? Well, there's one lone pair around the nitrogen in the central atom, and then there's one single bond, and then there's one double. But really, what I want you to think of, instead of single double, think atoms. Okay, there's 2 atoms. So each atom is a group. Here's one group, here's another group, and then the lone pair is the 3rd group. I have 3 groups that have electrons, and I want to spread them around. So what am I going to try to do? I'm going to try to minimize repulsion, right? So I'm going to spread them around, right? So here would be the lone pair, here would be the double bond and the single bond. And again, we talked this structure, this Lewis structure with 180-degree rotation in this 2D flat screen would give us a resonance structure, okay? So in this course, we are going to focus when there are 2, 3, or 4 groups. We can actually go beyond that. In other courses, we discuss the expansion of the octet because the D sublevel, that sublevel can actually add up to 10 more electrons. And when you have central atoms that are in the 3rd energy level or beyond, they can actually expand the octet and have more than 8 electrons around them. This course doesn't focus. So our focus is at most, we're going to focus on 4 electron groups, 4 single bonds, or 3 lone pairs in a single bond. That's the most. So let's think of it as, what if I have 2 groups? Okay, if I have 2 things and I want them to be as far away apart as possible, what would I do? 180 degrees, right? I want this over here and this over here. So that is an example of CO2. Carbon, the central atom, right, is bound to 2 other atoms. So the central atom has 2 groups, 2 oxygen atoms. I want the 2 oxygen atoms as far away as possible. What do? I put them away like this. 180 degrees is the angle. There's CO2, there's a Lewis dot structure. So it doesn't matter that there's, there's a double bond. It just matters that there's 2 atoms and they need to go far away. So this is referred to as a linear electron group geometry. It's linear because, it's like what it looks like. Forms a line. From the central atom, the 2 things are 180 degrees apart. And that's what this molecule would show right here. And you can see that I have the 2 double bonds to the oxygen, okay? What if there's 3 groups? Well, that's going to form what is referred to as trigonal planar and 120-degree angle. What do I mean? So if I have 3 things attached, just think a circle. Circle's 360 degrees. If I want to split that into even pieces, 3 things, 3 central angles, those angles are going to be roughly 120 degrees. So this is an example of formaldehyde. Formaldehyde is a molecule that has 3 groups around the central atom. So what are the 3 electron groups? Well, carbon's a central atom, and I have hydrogen, that's 1, another hydrogen 2, I have 3 groups. So I'm going to spread those 3 groups as far away as possible. That's going to give me trigonal planar. Now, why is that trigonal planar? Well, if I look, there's 1, 2, 3 sides. I could think of 3 sides. So there's the trigonal. And the molecule for something that's trigonal planar that has 3 groups is flat. So planar. So it's trigonal, 3 sides, planar, because it's actually a flat molecule. Okay. The hard one is when there's 4 electron groups. When there's 4 electron groups, when we draw the structure, we might think, oh, I got a line here, I got a right angle, right? And that would be 90 degrees. But in actuality, that's not true. And this is where Lewis dot structure, we need to be careful, right? So in a 2D model, it's true. It would look like, hey, this is 90 degrees. But in 3D, we're not limited to 2 axes, X and Y. We can actually expand that angle to a larger angle in 3D and form what is referred to as a tetrahedron. That's why the electron group geometry, when I have 4 groups, is tetrahedral. So how do I know I have 4 groups around the central atom? Well, carbon's a central atom, and there's 1, 2, 3, 4. And in 3D, I see that there's 1, 2, 3, 4 vertices that make a tetrahedron. So there's 1, 2, 3 lateral faces and the triangular base in this tetrahedron, which results in a tetrahedral. And that bond angle is actually greater than 90. It's 109.5. So you actually do need to know that there are 3 bond angles that we're focusing on in this course based on whether there's 2, 3, or 4 electron groups. If there's 2 groups, just think 180. 2 things, I want them far apart. If there's 3 groups, just think 120, right? One's going to go this way, and then 2 are going to go that way. If there's 4 groups, this is the hard one. It's the 109.5. So I always tell students, you know, they usually don't have problems with this. Just remember 109.5, okay? Now, I actually said that there is an option for people if you don't want to buy a model kit. Again, I really recommend the model kit, especially if you're going to take bio or biochemistry or organic or anything like that in the future. It'll help you. But if you just don't want to spend the $20, I get it. Then this website, if you click on this, it's a simulation from Colorado University. It is such a good simulation for students. I'm going to click on it. Hopefully it'll work. It's not. All right, there, whoops, other things popped up. But if you go here, the reason why I love this is now I don't even need a model kit. What I can do is I can click on this and I can kind of swing it around. And what I'm going to do is I'm going to eliminate everything. Okay. I just have a central atom. And remember, for this course, we're focusing on 2, 3, or 4. Okay. So, and we have what is called electron geometries. Okay. That's for the number of electron groups. And we also have bond angles. So I'm going to click on bond angle, and I'm going to click on electron geometry. Okay. And now I'm going to say, all right, I want to do like that CO2 molecule. And remember, with the CO2, I had 2 double bonds. All right. I'm going to do 1, 2 double bonds. And what I notice, it doesn't matter. What I notice here is if I have 2 things attached, it's 180 degrees. And I'm showing the bond angle here, okay? There's the 180. Now, if I remove that, I don't get to see that nice bond angle. I like to see that, right? And what I notice is it's calling it linear. It doesn't even matter, okay? It doesn't have to be 2 double bonds. It could be 1 single and a triple, right? So let's say that central atom was carbon. It still has the 4 bonds, just like in the CO2, but instead of 2 doubles, it's a triple and a single. I still have 2 things. Doesn't matter, right, how many bonds are in to each of the exterior atoms. It's just that I have 2 atoms, so they need to be as far apart as possible, okay? I always use the analogy, you know, when my kids, I have an older son and a younger, when they would fight, it doesn't matter that one was bigger than the other. I just put them apart like this. It's the same concept. I want to maximize repulsion by maximizing the angle, okay? So now what if I have 3 bonds? So we use the example of, well, this isn't formaldehyde, but there was a double bond and 2 single, like in formaldehyde. So we had 2 single to the hydrogen, but we also had 1 double to the oxygen. And what I see now is there's my 120 degrees, right? I can move this around. And now it's saying trigonal planar for my electron geometry, okay? And the other thing is when I rotate this, I can see that it's a flat molecule. So I dig that. If you don't, I wish this was around when I was a kid because I was cheap and I didn't buy the model kit. That's why I'm telling you, don't be mean. Of course, it was $45 back in 1988. It's only 20 in 2022, but you should probably buy it. But see how it's flat? That's what this shows you. Yeah. Now, what if there's 3, okay, or 4? So if I start with 4, right? Obviously, oh yeah, I forgot to mention this. If I only have 2 atoms, 2 dots are going to make a line. It's always going to be linear. I typically talk about when there's more than 2 atoms, because if there's only 2 dots, it's going to be linear no matter what. I mean, there's no other way to connect 2 things. So like 2 hydrogens, 2 all the diatomics that I had mentioned, they're all linear, right? Because if you connect 2 things, the only way to connect them is with 2 dots is a line. So that I didn't even cover because when we're doing the valence shell electron pair repulsion theory and electron group geometry, we're looking at a central atom with 2, 3, or 4. Okay, so here's the 2, still linear. If I had a third, that's now trigonal planar, the 120. But when I add the 4th, what do we see? We see 109.5. And man, this is such a good simulation right here. I can twirl this around and I can actually really see that tetrahedron, okay? So this is a really nice tool for you guys, and I hope it helps you out, okay? So I'm going to minimize that and go back to, whoops. Sorry, my screen's being covered. All right, so let's move on. Some of those Lewis dot structures, though, they actually had lone pairs. And the lone pair, in actuality, affects the repulsion. And why is that? Well, if I have 2 electrons that are being shared between 2, when they say nuclei, what they should be saying is here's 1 atom, here's another atom. In this atom, there's a nucleus with positive charge and same with here. So they're pulling these electrons and they're kind of spreading it over a larger area. If there's only 1 nucleus and then there's 2 electrons, these are going to be pulled in a lot more, okay? So what happens is the electrons are pulled rather than spread over 2 atoms, and when they're pulled closer to that central atom. Now, what does that mean? Well, they actually distort the bond angles and make them smaller than what you would expect. So what do I mean? So let's say I have 3 things attached, right? 3 atoms. However, if one of them is not an atom and it's actually a lone pair, instead of being spread over 2 atoms, the central atom and an exterior, now those 2 electrons are not being spread and they're concentrated over the central atom. So what does that mean? Because these electrons are closer to the central atom, there's a greater, there's a greater repulsion, and that lone pair right here, because there's a greater repulsion, is pushing this bond and this bond more. So there's a squeezing in that angle. So it makes it slightly less. So what do I mean? Well, we'll look at the electron group geometry tetrahedral. So what do I mean by tetrahedral? I have 4 groups, 4 electron groups. So my electron group geometry, so I'll put that, my electron geometry is tetrahedral, okay? So if I have all 4 as atoms, then they're spread out and the angle is 109.5, okay? However, if in the case of ammonia, one of the groups, because what they're not showing you here, okay, is there's a lone pair. The reason why they're not showing you is typically there is a difference between electron group geometry and molecular geometry. Molecular geometry only looks at the atoms. So all of these have 4 groups. So all of their electron group geometries are tetrahedral. For molecular geometry, this methane is still tetrahedral. The molecular geometry for methane, NH3, now this doesn't look tetrahedral because I'm not taking into account the lone pair. So that doesn't look the same. So this molecular geometry is pyramidal. Now remember, I only want you memorizing 3 angles, 180, 120, 109.5. Tetrahedral, the electron pair geometry gives me a 109.5 angle. I said when there's a lone pair sitting on the central atom, it distorts the angle because it actually squeezes this down more. So that squeezing causes this angle to get smaller. So a pyramidal molecular geometry, even though it has 4 groups, what are the 4 groups? 1, 2, 3 hydrogen atoms and 1 lone pair. Its angle, and this is only for methane. So not all pyramidal molecules have a bond angle of 107, but what I do want to show you, it's less than 109.5. I just want you to know that it's less than 109.5. So you're going to use the inequality. The bond angle is less than 109.5, and the alligator points to the bigger meal. So 109.5 is bigger than the bond angle for this pyramidal molecule. Okay. Well, what about water? Again, water, it's groups. It still has 4 groups. What are they not showing you? They're not showing you the lone pairs. Okay. So that's the drawback with these models. They don't show lone pairs. Now, that's why I'm starting with methane. I removed 1 atom, but I left the 2 electrons to say, hey, there's still a pair here, but now it's sitting closer. So that's where there's the distortion. Well, what about for water? Well, the oxygen actually has 2 lone pairs. So that means that the bond angle between these 2 hydrogens, there's even a greater repulsion because of the concentration of lone pairs, squeezing this to make it even smaller. And that's 104.5. Again, I don't want you to memorize that. Not all, and the molecular geometry for water is called bent. Okay, so the electron group geometry is tetrahedral, which means I have 4 groups. What are the 4 groups? 1, 2 hydrogens and 1, 2 lone pairs. That's 4 groups. The electron group geometry is tetrahedral because there's 4 electron groups. So the bond angle is roughly 109.5. However, because there's lone pairs, there's greater repulsion and a distortion. So it's less than 109.5. That's all I want you to remember. And that the name is the molecular geometry is bent. Okay. So some of you are like, oh man, you're really expecting a lot if you think I can, know all this. And I know, but this is part of the chem. It's tough. So here is why I like this PhET simulation. If I go to the PhET simulation, okay, now I want to go to real molecules. Okay, when I click on real molecules, what I know, whoa, look, right off the bat, it says H2O right here for the real molecule. And it's showing the lone pairs, which is good. Okay, so you can kind of see the lone pairs, right? You see those lone pairs. So what does that mean? I have two atoms. Here's one hydrogen. Here's another. There's two lone pairs. So my electron group geometry is tetrahedral. However, when I'm talking about molecular geometry, we're only looking at atoms. So I would remove the lone pairs. And now that's why the molecular geometry is called bent. So that's the difference. When there are lone pairs in the central atom, the molecular geometry is different than the electron group geometry. And what else is different? There's a slight deviation in the angle. So again, this is 104.5 instead of 109.5. You don't need to memorize that. I just want you to know that it's less than 109.5. If I go to the ammonia, where's NH3? Ah, right there. And I'm going to remove everything, okay? So with the ammonia, actually, I'm going to show the lone pair. There's 4 groups, 3 hydrogen atoms, 1 lone pair. So because there's 4 groups, my electron group geometry is tetrahedral, which means the bond angle is going to be derived from 109.5. However, one of the groups is a lone pair. So in reality, the molecule doesn't look tetrahedral. It's trigonal pyramidal. The bond angle isn't quite 109.5. It's less than 109.5. Okay. So what we're noticing is when there are lone pairs, right? When there's a lone pair, the bond angle is distorted and the molecular geometry changes its name from the electron pair geometry. When there is no lone pairs on the central atom, we go back to where we were before. So here's methane. I have 4 groups. They're all hydrogens. The bond angles are all 109.5 because 4 electron groups. The tetrahedron is the best way to maximize the bond angle and minimize repulsion. The electron geometry is tetrahedral, but so is the molecular geometry. Why? The molecular geometry is the exact same as the electron group geometry if there's no lone pairs on the central atom. So there's no lone pairs, so they're the same. The bond angle is the same too. It's 109.5. Why is that? Because there's no lone pairs. Okay, so that's the key. If the central atom has a lone pair, then the molecular geometry won't be the same like it is for methane. There's no lone pairs, all atoms, it's the same. The angle's the same. As soon as I have a lone pair, there's distortion. Now that angle's a little bit less. And even though the electron geometry is tetrahedral because there's 4 groups, I don't call it that because we don't look at that when we say the shape, and it's just trigonal pyramidal. It's the same when I go to, again, the H2O, right? Still 4 groups because 2 lone pairs, 2 atoms, right? The electron group geometry is tetrahedral, but the molecular geometry is bent. Why? Because we're only looking at the atoms when we do the molecular geometry. The bond angle is less than 109.5. So that's where this chart is. This should be in your book. And what you'll notice is whenever there's a lone pair on the central atom, it's a lone pair on this structure, there's a lone pair here, there's lone pairs here. What we notice is there's a less than symbol because of that distortion. We also know that the molecular geometry is a different name than the electron geometry. When is the electron geometry and the molecular geometry have the same name? When there's no lone pairs on the central atom. So CO2, carbon has no lone pairs. So electron geometry, molecular geometry is the same. There's no distortion, it's 180. So that's 2 groups. What if there's 3 groups? Well, if all 3 are bonds to atoms and there's no lone pairs, then the electron geometry and molecular geometry are the same. There's no distortion, it's 120. But as soon as I put a lone pair, molecular geometry has a new name and there's a distortion. What about 4 electron groups? Again, the bond angle is 109.5 because that's a 4 groups electron geometry tetrahedral. If there are no lone pairs, like in the case of methane, the molecular geometry is tetrahedral and there's no distortion. But if there's one lone pair, the electron geometry is tetrahedral, but the molecular geometry is pyramidal and there's the distortion. If there's 2 lone pairs, it's bent and there's the distortion. Okay. So let's do a quick check, right? Can we determine the molecular geometry for CCl4 from drawing the Lewis dot structure? Okay. So I'm just going to draw the dot structure first because this is based on identifying it once I have the Lewis dot structure, what the molecular geometry is. So you can practice that by pausing it. But basically, carbon tetrachloride, right? It's got 4 chlorines. So 4 electron groups because 4 atoms. So 4 electron groups, 4 atoms. What is that? Well, it's electron group geometry of tetrahedral. Since there's no lone pair on the central atom, the molecular geometry is also tetrahedral, and the bond angle is 109.5. So let's do formaldehyde, right? So here's formaldehyde. So how many electron groups around the carbon in formaldehyde? 3 atoms. 1, 2, 3. So that means there's 3 groups. Since there are no lone pairs, right? The 3 electron groups are atoms bonding pairs. There's no lone pairs, so as a result, there's no distortion in the angle, and the molecular geometry is the same as the electron group geometry. Last but not least, we have the CO2, and we see that this carbon has no lone pairs, and it has 1, 2 electron groups, 2 atoms, so it's linear, both for electron geometry and molecular geometry, and there's no distortion of the 180. You can always refer to the PhET simulation for more practice. Well, earlier we did the carbonate, which was this. This is what we opened up for review. But I'm going to do the ozone. So O3. And I'll even start it from scratch, right? There's 3 oxygen, there's 6, I have a total of 18 electrons. They're all the same atom, so oxygen's in the center. I have to bind them, so -4. There's 14, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, -12. I have 2 left. Where do they go? On the central atom. But the central oxygen doesn't have a lone pair, so what do? I can form a multiple bond. Could I do a rotation here? Of course. So how are these 2 Lewis structures related? They are resonance structures. But more importantly, what we really want to get at is what are their molecular geometries? Okay. So for ozone, right? My chicken scratch, I'm sorry. Let me erase my chicken scratch here. Try to give you the clean. So if I look, ozone has 3 electron groups. Why is that? 1 lone pair right there and 2 oxygen atoms. So 3 groups. So where am I going to be located? One of these. But one of the groups is a lone pair and two are atoms. So what does that mean? Even though it has three groups and it's trigonal planar, for the electron group geometry, because we want to spread the three groups, this lone pair causes greater repulsion here and squeezes this angle, and that's why I get less than the 120. And also, when I look at the structure itself, they don't show the lone pairs on the molecule, on the molecular models. It just looks like that. So that's why it's called bent. The carbonate, right? It also has three electron groups, but in this case, they're all three atoms. So there are no lone pairs. So the electron group geometry and molecular geometry are the same because the central atom has no lone pairs and there's no distortion and it's 120 degrees. And again, for practice, you can use a PhET simulation or just draw your Lewis structures. So now what we want to do is we want to predict all the exercises from the last lecture where we did the Lewis dot structures and we drew Lewis dot structures to predict their electron geometry and molecular geometry around the central atom. So my EG and my MG. So we've already drawn this. So I'm going to go quickly because the key here is to identify the electron geometry, molecular geometry. So this is what we had last time. So how many electron groups? Well, there's 4 groups. Why? 2 lone pairs and 2 atoms. So this is tetrahedral. However, there's 2 what? Lone pairs. So 2 lone pairs and 2 atoms make it bent, just like water, H2O. Now we go to silicon tetrafluoride. With silicon fluoride, I'm going to omit the lone pair. I'll just do it. So here's silicon tetrafluoride. How many groups? 4 groups. So the electron geometry is tetrahedral. They are all atoms, no lone pairs, so the molecular geometry is also tetrahedral. Okay? Where is it different? PCl3. If you remember from last time, this is what we had. So 4 groups, right? So tetrahedral. What are the 4 groups? Well, we have 3 chlorines, 3 atoms, and 1 lone pair. Well, because there's a lone pair, the molecular geometry is different. What is that? Pyramidal. Carbon, right? Disulfide. How many groups around the carbon? 2 groups, 2 sulfurs. So that's linear. And the central atom has no lone pair, so it's still linear for molecular geometry. Nitrate. This is what we did last time. You could look at your notes. If you're taking notes, it'll be helpful. So it's giving me, okay. So there I have how many groups? 3 groups. So that's trigonal planar. Because all the groups are atoms, there are no lone pairs, it's also trigonal planar. There's sample exercise number 6. What happens if there's more than one central atom? Because remember, I was drawing acetic acid and things like that. That does happen. So now I have to look at each individual atom. So what are my central atoms? Well, all the hydrogens are on the exterior. See how there are only single bonds on the outskirts? So that means I have 2 central atoms. I have this carbon and I have this oxygen, okay? Now, I only want to look at molecular geometry, I'm going to say, okay? So the molecular geometry to the carbon, there's 4 bonds, 1, 2, 3, 4, all atoms. So that would be 4 atoms, tetrahedral. Now the oxygen, it has 4 groups. So the electron group geometry is tetrahedral, but it only has 1, 2 atoms, and the other 2 groups are lone pairs. So that makes this bent. So in 3D, that's what it would look like. Now, unfortunately, the PhET simulation is only good for single central atom species. So there is another link that I have here that you can utilize, which is MolView. If it actually pops up. Oh, there it is. Okay, good. Yay. So there you go. I'm going to close this. Now, when you first see it, it does this gnarly structure. Don't worry about this. I'm just going to, no one's expecting you to know this stuff yet. So we can just do away with it. Get rid of that. Okay. So what did we have? We had a carbon. Boom. The carbon had 3 single bonded hydrogens. So I press single bond, I go to hydrogen, I go 1, whoops, something happened there. I didn't touch the carbon. 1, 2, 3. But it had the 4th bond to an oxygen. So now I go oxygen. And then the oxygen had an exterior hydrogen attached to it. Oh, you're better. Now, when I go to render this from 2D to 3D, what I see right here, what I can see is, there you go. I have the, tetrahedral arrangement in this carbon right here, and I have that bent shape. Right, so tools. I don't really want to spend too much time on this. You guys are more than welcome to kind of look at this. I mean, there are a lot of useful things like polarity and things like that. I'm forgetting what this is saying right here. Oh, they used to do it where you could do, yeah, oh yeah, here. Bond dipoles. They used to do that. Oh, there it is. There's the dipoles. I'll talk about what that is. You could also show the net dipole, overall dipole. So we're seeing that the dipoles on the side of the oxygen. I'll explain that. We also see all the dipoles pulling in different directions. That's why this is a polar molecule. And there's more stuff. There's the angles. But that's not the important thing. I just wanted to say, if you want to use something to draw in 3D instead of purchasing a molecular model kit, there are really nice simulations for you that are available online. The difference between this structure and the prior ones is with the PhET simulation through Colorado EDU, which I think is the easier, better one, actually, especially for this course, it's single central atoms. The MolView allows you to expand it and get into the organic and biochem type of molecules. So it's got some advantages there. But I had mentioned polar and non-polar. Okay, so what we have to realize is with covalent compounds, and remember, covalent, non-metal, they're sharing electrons, okay? And that's what we're doing a really good job with Lewis structure, is drawing these covalent bonds, right? Because we're drawing lines to show sharing of electrons, bonds. That's what the Lewis structure is great for. Covalent bonded structures, whether they be covalent compounds or polyatomic ions. But it's not reasonable to think that all the atoms out there can pull on these electrons when they're trying to share them the same. I mean, it's like relationships. No, there's not always perfect equal sharing, okay? So what does that mean? Well, unfortunately, some atoms pull a little more, so other atoms lose a little bit of that sharing of electron. They give a little more, well, because the other one's pulling and taking a little more, even though they're sharing. So it's not a complete electron transfer like with metals losing and non-metals taking in ionic compounds. Because they're both non-metals, they're sharing, but they're not always equal. So how do we determine who's the best at kind of pulling the electrons away in this tug of war? Well, here's another periodic trend. So in chapter 4, we talked about the periodic trends of atomic radius. Atomic radius, the basic size of the atom, based on the number of energy levels and orbitals. We talked about the periodic trend of ionization energy. How hard is it to take away an electron from an atom? Well, as the atom gets bigger and the valence shell is further from the nucleus, it's easier to take that electron away. And as I go from left to right, I'm in the same energy level, but as I go to the right, I have more protons. So it's harder to pull it as I go right. So the lower left corner has the weakest ionization energy. It's the easiest to pull the electrons away and form positive charges, cation, positive charges, and are the most metallic in character. Well, now we're looking at electronegativity, right? Instead of how easy is it to remove an electron or the metallic character, it's like, how good is it at tug of war? So it's the exact opposite. Instead of going to this corner for being kind of the most metallic, now I want to go to this corner, and these are the best at tug of war. Why? They're small, so that their valence shell is really close to the nucleus, which has the positive charges pulling. Just makes sense. Like in tug of war, if you're all stretched out like this, it's harder to pull than if it's really close in. So no one expects you to memorize these electronegativity values. It's not necessary, okay? But what we're seeing is as I go from left to right, electronegativity values increase. We see that fluorine's a 4.0. As I go down, it decreases. And we see that this corner, cesium's only a 0.7 electronegativity value, where fluorine's like the king of tug of war. Now, a lot of people ask me, why are these noble gases? They don't have one. They don't pull electrons very well because they're stable. They don't form bonds. So we're primarily looking at who's forming these bonds. So this pulling of electrons creates what's called a dipole moment, okay? So it is a dipole. What do I mean? It has two poles, a positive and a negative pole, because there's unequal sharing, and we create partial charge. So in covalent compounds, there's polar bonds and non-polar. Polar bonds are when there's unequal sharing. Non-polar is equal sharing. So one example of a polar bond is oxygen to hydrogen. When I look at oxygen, and I'll draw it because this is just showing, this is actually our representation of the electron distribution. So this is kind of the quantum mechanic model where all the dots is representing where you're going to find electrons and how often and how close. And we see that the electron distribution is much larger around the oxygen than the hydrogen. That's why there's this more dots. So in this oxygen-hydrogen bond, the reason why there's more dots or a greater likelihood of electrons being over by oxygen is it has an electron negativity of 3.5. The hydrogen has an electron negativity of 2.1. When I subtract that, that's a difference of 1.4. That's a big difference. So what does it mean? The oxygen's way better at pulling the electrons in that bond. So it creates what's called a dipole. What do I mean by a dipole? A slightly negative end and a slightly positive end. In that mole view, they were using arrows. The arrows show where the electrons are being pulled. So the oxygen is more electronegative. It's pulling the electrons, and the hydrogen's losing. So the electrons are going towards the oxygen, greater electron density, and the tail of the arrow looks like a little plus sign because the hydrogen, as the electron is being pulled away from it, is almost becoming positively charged. It's a partial positive charge. So what does that mean? Well, we have different bonding types based on electronegativity difference. And before we were saying, all right, there's ionic, there's covalent bonds. So here's ionic. Here's covalent. Okay. Ionic, a complete electron transfer. Why? Well, one's so good with electronegativity and pulling the electrons, the other one just lets go. So like sodium has 1 valence electron and chloride has 7. But what happens is the sodium gives it up. Why? Why does the sodium give away its electronegativity? It's a 0.9. Chloride's a 3.0. So 0.9, 3.0, that's a difference of 2.1. That's a big electronegativity difference. That falls under an ionic compound. You do not need to calculate that. You know that ionic compounds are metals and nonmetals. Sodium is a metal, chloride's a nonmetal. Boom, sodium chloride is ionic. Okay, that's all you need to know. Covalent is a little tricky because instead of, the metal and the nonmetal, typically in covalent bonds, you have nonmetal with nonmetal. So it's a little harder. So the way it works is there's kind of a degree of covalent, and there's 2 camps. So under the covalent bond umbrella, there's what's called nonpolar and polar covalent. Nonpolar means equal sharing, right? So the electron distribution is pretty much distributed equal between the 2 atoms. Polar is unequal. One's pulling more than the other. That was the example where I had the oxygen bound to the hydrogen, creating this partial positive, partial negative. The electronegativity difference for that was a 1.4. It falls between 0.4 and 2.0. That makes it polar. What I want you to know is the further apart atoms are from each other, the more ionic they become. Now, if it's a metal and a nonmetal, it's ionic. You don't need to know the electronegativity difference. But when we're dealing with covalent and they're all nonmetals, just realize the further apart they are, the more polar they become because there's a bigger electronegativity difference. The closer they are, the more they're likely to share equally because they're closer, they're more similar in their ability to pull electrons. So what's an example? Well, any diatomic, a hydrogen bound to a hydrogen. Well, and you don't need to know the electronegativity differences. I'll just show you though. 2.1 minus 2.1 is a difference of 0. You don't need to know that. You just know that hydrogen and hydrogen, neither is pulling more than the other. The difference is 0. It doesn't matter if you had chlorine to chlorine, which is, 3O minus 3O. It doesn't matter. You don't need to know that. You just know that if it's a diatomic, the difference is 0. The only non-polar bond that's covalent that I want you to know between 2 nonmetals is carbon to hydrogen. Now, why? That is a critical bond for organic and biochemistry. I said earlier that your proteins, nucleic acids, your lipids, and I'm forgetting one. Why am I? Carbohydrates. The carbon skeleton's the backbone, but what's attached to the carbon other than other carbons is hydrogen. So I want you to realize that the difference in electronegativity between the carbon, which is 2.5, and the hydrogen, 2.1, is 0.4, which means the carbon-hydrogen bond is nonpolar. So when I'm looking at covalent bonds, which are non-metals with non-metals, If there's a slight electronegativity difference to 0, it's nonpolar because it's equal sharing. The ones that I want you to know is if I have a carbon-carbon bond, that's got to be nonpolar because they're the same atom, right? Hydrogen, any of the diatomics, that's got to be nonpolar. Remember I drew, the peroxide? This bond right here is nonpolar. Now this bond is not, okay? That's why this is a, polar molecule, but the oxygen-oxygen bond is nonpolar. It's going to be 0. Okay, so that bond is nonpolar. So when is it going to be polar? Pretty much all the other times. You're pretty much going to have it polar. So this is just showing that distribution of the oxygen-hydrogen bond that I already showed. So for you, when you're drawing these Lewis dot structures, now you have to actually think a little more. You have to be able to do the, this is tough, and I get it. You got to be able to do the 3D molecule from the Lewis dot structure, but now you got to determine polarity based on electronegativity differences. So what does that mean? Well, I'm going to try to make it easy. A molecule can have polar bonds, but still be nonpolar. And I know you're probably going, that doesn't make it easy. So what's important is the orientation of the bonds. So if there's a symmetry in the bonds, all those dipoles, those little arrows that I was showing, they're going to cancel each other out, and you're going to have a nonpolar molecule. If they don't, if it lacks symmetry, if the molecule is asymmetrical, it'll be polar if it has polar bonds. So molecules with polar bonds may or may not be polar. Non-polar molecules will be symmetrical. So you have to look at the symmetry of the molecule. So remember CO2. This carbon-oxygen bond is polar. Oxygen's 3.5, carbon's 2.5. It's a difference in electronegativity of 1. That's more than 0.4, but less than 2.0. That's polar covalent. So there is a partial negative here, partial negative, partial positive, but the dipoles are equal in magnitude, but opposite in direction. What do I mean? The molecule's symmetrical. There's only 2 things attached to carbon. They're both the same atom. So it has symmetry. So even though the bonds are polar, the molecule is nonpolar because it has symmetry. It's symmetrical. So is there a case where polar bonds will actually give me a polar molecule? Of course. If it's unsymmetrical, actually you should just say asymmetrical. Where's that? Water. So again, these are polar bonds. I have 3.5 to 2.1, a difference of 1.4. But what's important, because the 2 lone pairs up here, this molecule of water is bent. And when it's bent, these dipoles are not, and actually the direction should be pointing towards the oxygen. Doesn't cancel out. In fact, if you ever take vectors, and you do head to tails for your vectors and count it, it creates an overall dipole that's going towards this oxygen. So because this lacks symmetry, why does this lack symmetry? There's 4 groups, and they're not all the same. 2 are hydrogen, but 2 are lone pairs. So this has polar bonds and is a polar molecule because it lacks symmetry. So how are you going to predict it? Draw the Lewis structure, then determine the molecular geometry. But more importantly, look at the molecule to see if the bonds are polar. Okay, and how do you do that? No, typically they're going to be polar bonds. But more importantly, if the molecule, right, is symmetrical, it's nonpolar. But if the molecule lacks symmetry, it's going to be polar. So this is symmetrical. Why? The 2 things attached are the same, nonpolar. This is not symmetrical. Why? There's 2 lone pairs up here. So the 4 groups are not the same. So it lacks symmetry. Someone might say, well, what about the carbon? There's no lone pairs on this central atom. Remember, we drew this now a couple times, so don't get confused. There's no lone pairs on this. This has 1, 2, 3, 4 bonds. It has an octet. This oxygen has 1, 2 bonds. That's only 4 electrons. That's why it needs 2 more groups, the 2 lone pairs. That's why it lacks symmetry. That's why it's polar. So let's look at hydrochloric acid number 1. Are those going to pull equally? No. It's a covalent bond. How do I know that? Well, it's 2 nonmetals. Are they the same? No. So that means one's going to pull better than the other. Which one? Chlorine. It's closer to the fluorine. Remember, fluorine is the best at pulling. So this is going to be a polar molecule. Why? It lacks symmetry. Number 2 is tricky because when you look at it, you'll be like, that's symmetrical. Well, we're forgetting. There's a lone pair. So its electron group geometry is tetrahedral, right? Even though we drew it pyramidal because we're not thinking about the lone pair. So because the 4 groups are not all the same, one is a lone pair, that is polar because it lacks symmetry. Now, number 3, it's tetrahedral, both electron geometry and molecular. But even though those bonds are polar, all of the atoms are the same. They're all chlorine. So because they're all the same, it's symmetrical, it's nonpolar. Boron trifluoride, 3 bonds. Boron's an exception to the octet. Boron, like hydrogen and helium, doesn't want an octet. It's one of the exceptions. So boron just has 3 bonds. The 3 fluorines are all the same. This is nonpolar. If I look at this is basically chloromethane. You don't need to know that name, but basically there's 1 chlorine and there's 4 hydrogen atoms. So this is not symmetrical because not all the atoms are same. Because this lacks symmetry, this is polar. So you're going to use the symmetry of the molecule to determine whether it's polar or not. So can we predict whether these are polar or non-polar? So we've kind of already drawn these. So when I look at this, I see that 1 group is an electron group, or a lone pair rather. 1 electron group is a lone pair. So this lacks symmetry because it has 3 bromines, which are the same, but it has a lone pair. So this is polar because it lacks symmetry. Now this is new. So we're going to do this. We got S2Cl+. The sulfur is actually in the middle, right? Because the sulfur is more metallic. And then we're going to add 2 times 6 valence electrons for each sulfur. Chlorine has 7, but we're going to subtract 1 because there's a plus charge, which means I removed an electron. So I have 12 plus 6, I have 18 electrons. Sulfur is in the middle, and then I have my chlorine. So 2 bonds minus 4, I have 14 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 2 electrons left. I add them as a lone pair. I have no more. The central atom doesn't have an octet. I'm going to choose, because of bonding patterns, to move the double bond from the sulfur, not the chlorine, because group 7A likes to have 1 bond, 3 lone pairs. Group 6A, like oxygen, likes 2 bonds, 2 lone pairs. Now, why am I drawing this with an angle? The electron group geometry, so how many electron groups? 1, the lone pair, 2, the sulfur, 3. So the electron group geometry is trigonal planar. However, the molecular geometry is bent. Why is it bent? because the lone pair on the central atom. The bond angle is less than 120 because when there's three groups, it's 120, but this is squeezing this angle to less than 120. Is this polar or nonpolar? This is polar. Why? It's not symmetrical. You honestly didn't even need to draw this to see that, but it's good because you might have thought that this was symmetrical if you didn't take that into account. But this lacks symmetry. The three groups are all different, so this is polar. So then last but not least is ammonium, which is basically this structure. How did I get that? 5 valence electrons for nitrogen. There's 4 hydrogen, each has 1. The plus charge, I subtract 1. So 5 plus 4 minus 1 is 8. So 4 hydrogens, 1 bond, 2, 3, 4. 2 times 4 is 8. There's no more. All 4 groups are the same. So this is a symmetrical molecule, and this is nonpolar. So you can see here, we are taking our Lewis dot structures and our molecular geometry to determine whether or not a molecule is polar or nonpolar. We'll see that this is really important in future discussions when we get to solutions and determine whether or not something is soluble in water or insoluble, whether I have a homogeneous mixture or a heterogeneous mixture, because later on we'll talk about mixtures. Right now, we're still dealing with pure substances, and we've covered atomic structure and we're in molecular structure, and that's why we're doing Lewis dot structures to show the molecules for covalent compounds. In the next lecture, I will continue using molecular structure and determining polarity to determine the type of intermolecular force. The intermolecular force is not the bonds within a molecule. So ionic and covalent bonds are intra, they're within. Intermolecular, like an international flight, is between countries. Intermolecular forces are between molecules. And our next lecture, we'll talk about the intermolecular forces that influence compounds, boiling point and melting point and things like that. And that's going to be based on whether or not the molecule is polar or nonpolar. So again, thanks for your patience. I'll see you next time in our last lecture for chapter 6, compounds and their bonds. Thanks so much for watching. I appreciate your patience.